solid liquid interface. Now, here we can look into the different type of the solidification mode and structure. So, it is also necessary to mention that although these two parameters G and R, so G and R, these two parameters, that means temperature gradient and growth rate, they actually mathematically define the mode of the solidification at the same time, and also define the rate of the cooling. That rate of the cooling is decides basically that whether it is fine structure or whether coarse structure exists during the produced during the solidification process, and solidification mode decides what is the type of the, whether it is planar, 4 types of the planar or cellular, dendritic, columnar dendritic or equi-X dendritic kind of structure. Now, if we see that 4 different types of mode is better, from this figure we can see that there is a 4 type of solidification mode: planar mode, cellular, columnar dendrite, equi-X dendritic structure. Now, here you can see that increasing the constitutional supercooling is transform the structure from planar. So, that means very low amount of the constitutional supercooling promote to the formation of the planar kind of the solid liquid interface. But if the constitutional supercooling is very high, maximum in this case, they actually promote the structure like equi-X dendritic structure, it will try to produce. Now, graphically also we can see that here the vertical line, the solid liquid interface, and that side the equilibrium temperature reach, and this is the, this represents the actual slope in the curve. So, in the that curve, the time and the solid liquid the distance versus temperature, in that case the actual slope. So, here if you see that the temperature and actual slope, they are not interfering with respect to each other. That means, there is a minimum amount of the, or we can say there is no constitutional supercooling exist. So, that promote the planar kind of the solid liquid interface. The mode of the solidification is basically planar. Next, if the certain amount of the increment of the constitutional supercooling, then it cross the slope is less basically, and then there is a shaded zone that is marked by the black, the shaded zone, and that actually produce the cellular kind of the solidification mode. Cellular mode, in this case, that means there is a small amount of the constitutional supercooling exists. If you look into the third, that amount of the constitutional supercooling actually increasing, and that try to produce the columnar dendritic structure, and finally, the maximum amount of the supercooling that produce the equi-X dendritic structure. So, depending upon the amount of the constitutional supercooling, the solidification mode basically changes, or solidification mode can be decided. Now, here also other comments that the dendrites and the liquid phase coexist is called basically the Musi zone. So, in that zone where the dendritic formation of the dendrite and the liquid, they actually coexist, that is the normally called the Musi zone, and that Musi zone is basically in between the temperature between the solidus and liquidus temperature. So, at very high degree of constitutional supercooling, it is very obvious that the Musi zone becomes very wide. So, that zone becomes very wide, or at the other way, if low degree of the constitutional supercooling, there is almost no Musi zone, or Musi zone not very wide, small. So, here from that with respect to the point of the view that with the degree of the constitutional supercooling, we can predict at least the what are the type of the solidification mode, whether it is planar, cellular, columnar dendritic or equi-X dendritic structure. Now, here we like to mention that the two parameters, the temperature gradient G and the growth rate R, affects the solidified microstructure. So, two different ways. So, by combining these two parameters, the temperature gradient and growth rate, here you can see the product of G into R, this actually known as the cooling rate. If we dimensionally check it, then that G is the temperature gradient, temperature by length and r is the growth rate. So, length by time. So, in that respect the length by time is basically temperature by time, that actually represents the cooling rate. At the same time the ratio G by R actually determines the solidification mode, that already we have discussed, that depending upon the G by R ratio we can define the mode of the solidification. So, this combining these two G R and G by R, if you try to represent the one axis, the x axis the growth rate R and temperature gradient is the y axis, it is the G. So, this combining these two we can find out that different solidification mode this way, that planar, cellular, columnar dendrite and equi-ax structure. So, high G by R value that actually promote the kind of the planar structure, or at the same time low G by R ratio that actually promote the equi-ax dendritic structure, dendritic solidification mode. But if you see that from the graph also, if now we try to incorporate the effect of the cooling rate also. So, here this line that represents the rate of the cooling, so G R, and so first line alpha 1 that represents the low cooling rate, and if you see the alpha 2, the second line, this is represents the cooling rate on this graph, that represents the high cooling rate. So, if cooling rate is very high, overall microstructure is very fine. If cooling rate is low, the overall microstructure is not the coarse structure. So, basically higher cooling rate we can expect the fine structure, and lower cooling rate we can expect the coarse structure. So, greater G R, G into R, that means G into R, that means greater cooling rate, that we can find out the very fine solidified cellular kind of dendritic structure. If we see from this figure also that most of the structure exists in this case, that either cellular or columnar dendriting, and planar and equi-ax is the more two extreme cases here, but in general cellular and columnar dendritic structure exist, and it becomes more finer structure if cooling rate is very high. That means, it is beyond that zone, the second line corresponds to alpha 2. So, basically alpha 1 equal to 1 G 1 R 1, or alpha 2 is basically another value of G into R. So, from this figure we can explain also quantitatively that whether it is fine structure, coarse structure, at the same time what is the solidification mode, or what is the solidified structure, whether it is very planar, columnar kind of structure, dendritic, equi-ax, and all this kind of information we can get by analysis of this kind of figure. Now, after solidification mode, we will try to look into the discussion on the weld microstructure. So, grain structure actually affects the susceptibility of the solidification cracking. So, it is very much linked with that, and finally, grain structure also define the mechanical property. So, it is it is necessary to link that what is the final microstructure and probably what is the expected mechanical properties, or whether there is any solidification cracking may occurs or not. That kind of information can be get if we analyze the mechanism of the grain structure or maybe weld microstructure formation during the solidification process. So, one important aspect of the growth in the fusion zone of the welded structure, that is called epitaxial growth at the fusion boundary, and this epitaxial growth basically happens in case of the autogeneous fusion welding process. So, if we use some filler material that actually destroy the epitaxial growth mechanism, maybe in that case some other mechanism can be better to explain the phenomena of the grain growth. So, epitaxial growth we can see that molten metal first is in contact with the solid with the base metal, then grain growth initiates on that boundary or at the solid liquid interface, and it proceeds towards the weld central line. From the figure also it is very seen that very obvious that welding direction is there, and the weld pool from the oil pool liquid oil pool and that interact with the base metal. So, from that interface it growth happens one particular direction. So, that this type of growth is basically called the epitaxial, first nucleation and then growth. So, if you see that FCC, BCC crystal structure, they have the kind of columnar dendritic structure actually grow in the 100 direction. So, Miller index of this 100 direction. So, that actually observed in case of FCC and BCC material. Now, if you see here that if you use the filler material, then weld metal composition changes and that actually leads to the different type of the crystal structure for the weld and the base metal. So, that adding the filler metal doesn't promote the epitaxial growth, and then new grains and nucleates basically forms at the fusion boundary when there is a addition of the other alloying elements, or maybe you can say that with the addition of the filler material during the welding process. So, during solidification the grains tends to grow perpendicular to the weld pool boundary, but the reason for that, there is a maximum temperature gradient actually exists along this direction, and then sometimes the columnar dendrites or cellular cells or cellular structure within each grain also grow in the within grain that try to grow in the easy growth direction. So, that means that different type of crystal structure material having the easy growth direction. For example, the FCC structure, the 100 is the easy growth direction, and we can observe specifically for the aluminum alloy and austenitic stainless steel, they are having this direction. BCC material also having the easy growth direction is 100. That is why if you look into the one unit cell, the 100 is basically along the one of the edge, along the edges. So, the carbon steel, ferrite, stainless steel, this type of materials also having the easy growth direction for the BCC material as the along the edge of the unit cell, that means 100 direction. Then in case of hexagonal close pack also having the easy growth direction, and that hexagonal close pack structure titanium and I think magnesium, and body center tetragonal structure tin also having the easy growth direction is 110, that means along the phase diagonal of an unit cell. So, different type of materials may have the different easy growth direction, and typically the epitaxial growth nucleation, not only growth, maybe first nucleation starts and then growth process starts. So, that epitaxial growth mainly happens probably the pure metal and during the welding process, and that along the normal to the phase boundary, because the driving force, the epitaxial growth in specific direction, probably the maximum temperature gradient along that direction. But the conclusion from here is that if we add the filler material, then the epitaxial growth may not be possible in that case. Now, what are the effects of the welding parameters on the grain structure? And just if we try to look into that, is that if we look into the actual welded structure, what type of microstructure we can expect during the welding process at very high speed probably and at very low speed. So, if we see that high welding speed, the typical nature of the weld pool forms, that is the elongated weld pool, or sometimes teardrops can also form. So, if you look into the first figure, that it is a high speed, that if it is a elongated weld pool looks like, and when the heat source is moved one specific direction during the welding process. So, here the growth or grain actually grow with respect to that weld central line and almost perpendicular to the weld central line, but if it is very high speed, then it becomes axial, exactly perpendicular to the weld central line. And if we gradually reduce the welding speed, that means if very low speed, it takes the curvature and with respect to the weld central line. So, and from that weld center lines make a curvature and goes towards the outer periphery of the weld pool. So, these are the typical grain structure generally observed during the welding process. Now, if in case of low welding speed, the welding pool looks like the elliptical form, and trailing pool of the boundary of the teardrop shape, that means it is a very high welding speed. The weld pool is almost nearly straight, and the growth also happens perpendicular to that. But column work grains forms during these things almost the straight normal to the pool boundary. But in case of low speed, since the trailing boundary is of elliptical shape, then weld pool is basically make a curvature or make a curve, and the column work grains are also curved in order to grow perpendicular to the weld pool boundary. So, making the initial curve, so that and finally, it makes the final curvature, it is like that almost perpendicular to the weld line. So, these are the typical weld grain structure that actually